Doing it outside the church? We're getting married. Oh, I thought you were going to Orlando. I was like, actually, we make a little later. That's okay. When are you getting married?
Which one is this one?
This one. This is green.
It doesn't look green.
My name is Brian Thompson. I'm with the White team. We're going to go over two things: the steady-state operating curve and a step function for a voltage system. These are our teammates. We're going to go over the background and theory of the voltage station, our steady-state operating curve. Then we're going to get a step response. We're going to talk about results, conclusions, and some discussions. This is the background of the steady-state operating curve. Again, we have a motor that's hooked directly to the generator, and the generator output goes to some lights. So you have to have some place for the voltage to go. This measures the amount of voltage that's coming out. This would be our computer. We're running in here, and it goes through these things to tell the motor what to do. This is a block diagram of simplifying what's going on. We have our voltage system, which would be all the hardware in it. We input an input as a percentage of 0 to 100%, and our output comes out in terms of a voltage. This is an example at 60% of our input value. As you can see, we have a steady line at 60%. So the voltage the input parameter is constant. It takes several seconds to get up to a steady state operating voltage. And so we cut the graph off here, between here, to get an average of what this is. Here's a graph of some of the values that we have, getting our average and also the standard deviation. We had enough data points that we could use the standard deviation on this. And for this class, as you know, we're doing 2 times the standard deviation, not just 1 time the standard deviation. After we graph all of the individual data points of each run onto one curve, we chose this section to get a slope of the curve. The slope is 0.25. That's 2.25 volts per percent increase in voltage. Now moving on to the step function, where we have the voltage come in, the input value at 54%, and then we jump it by 11%. We wanted to see how the voltage would work. As you can see, it comes in steady and then immediately starts to rise. It gets to a steady state point. In here, we need to figure out what the T sub O, the dead time, is, and it was very, very, very short, just like 0.05 of a second. And you draw a line through here, as you know, and where that line crosses this line, the distance between where you initially start the change to where that comes, that's your value for T sub O. You then take 63.2% of your change of our voltage, you draw a line on here and then come down, and that line between that and where the dead time ends, that is your time constant. This is a graph that simplifies, showing how we got all this data. Again, T sub O is between when you first tell your system to change to the point where it starts to change. Then your time constant is 63.2% of your overall change. Where that hits, the distance between there and where your dead time ends. Your constant, your gain, is your total change in your voltage in this case, divided by the change of the input that it took to bring about that change. Now, in our examples, we have here some bar graphs. The blue is on step is the T sub O going up, and then the red is the T sub O going down. They're right side by side of each other. As you see, these are fairly close to one another, and this is called an outlier. Next one. This happens to do with the change of the input that we have. This is the time constant, the tau. And as you can see, generally, it's about the same. It's real short, less than 1/10 of a second. Again, we have some outliers here. Now here's the average gain. This is that K value. K, as you know, is the total change of your voltage divided by the change of the input. And there's quite a bit of variation between these different areas. You just can say that this area is not that stable. And our summary conclusions, we ran between 40% and 64% of motor input and resulted in 2 to 8 volt output. We tried at 65%, and for us it goes way outside our operating range, so we can't use 65%. The slope of the steady state operating curve came out to be 0.25. That's 0.25 volts per percent of input. We went over the step up and step down functions, and the concept of T sub O, tau, and K were introduced. Our T sub O, tau, and K varied so much in this that it was real hard to come up with a justifiable average for them. Thank you.
On that note.
Now we go back to green. The voltage system, I think you're going to learn, you may have already learned this by seeing 3 presentations today, is the most interesting system. What you're going to learn about this next system, it is the most boring.
Yes.
I can green on that other year. I think that's a good one. Yeah.
I don't mean to be critical. That's just,
Oh, it is very boring. It's
Yes.
just great.
it's great.
No, it's-